Hi, my name is Luc-Hugues and I'm going to be showing you conditional probability and the multiplication rule and how they coincide in this first segment of the video. So to begin, a conditional probability is the probability of an event occurring given that another event has already occurred. It's denoted as PBA and is read as the probability of B given A. So for our first two questions, two cards are selected in sequence from a standard deck. Find the probability that the second card is a queen given that the first card is a king. Assume the king is not replaced. In our second question, the table at the bottom left shows the results of a study in which researchers examined a child's IQ in the presence of a specific gene in the child. Find the probability that a child has a high IQ given that the child has the gene. Our solutions. Because the first card is a king and is not replaced, the remaining deck has 51 cards, which is also our sample space. 4 of these cards are queens, so the probability of B given A equals 4 out of 51, which is approximately, and this is very important because we are rounding up, so this is not an exact measurement, approximately 0.078. For number 2, there are 72 children who have the genes, so the sample space consists of these 72 children as shown at the bottom left. Of these, 33 have a high IQ, so the probability of B given A equals 33 over 72, which is approximately 0.458. Now for independent events. Two events are independent if the occurrence of one of the events does not affect the probability of the occurrence of the other event. Two events A and B are independent if the probability of B given A equals the probability of B, or if the probability of A given the probability of B equals the probability of A. Events that are not independent are dependent. So for our 3 questions, we have selecting a king from a standard deck, event A, and not replacing it, and then selecting a queen from the deck B. 2. Tossing a coin and getting ahead, event A, and then rolling a 6-sided die and obtaining a 6, event B. And for number 3, driving over 85 miles per hour, event A, and then getting in a car accident, event B. So for our solutions, the probability of B given A equals 4 out of 51, and the probability of B equals 4 out of 52. The occurrence of event A changes the probability of the occurrence of B, so the events are dependent. The probability of B given A equals 1 over 6, and the probability of B equals 1 over 6. The occurrence of A does not change the probability of the occurrence of B, so the events are independent. If you drive over 85 miles per hour and you get into a car accident, the chances of getting in a car accident are greatly increased, so these events are dependent. The multiplication rule. The probability that 2 events A and B will occur in sequence is the probability of A and B, which equals the probability of A times the probability of B given A. If events A and B are independent, then the rule can be simplified to the probability of A and B equals the probability of A times the probability of B. So, for our first 2 questions, 2 cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then selecting a queen. In our second question, a coin is tossed and a die is rolled. Find the probability of getting ahead and then rolling a 6. Because the first card is not replaced, the events are independent, so the probability of K and Q, king and queen, equals the probability of K times the probability of P, the probability of Q given K, which equals 4 out of 52 times 4 out of 51, which is 16 over 2,652, which is roughly 0.006. For number 2, the events are independent. The probability of H, or probability of heads, and 6 equals the probability of heads times the probability of 6, which is 1 over 2 times 1 over 6, which is 1/12, which is roughly 0.083. This completes the first segment of the video. For our second segment, we'll be going over mutually exclusive events and the probability of, the addition rule. So, two events A and B are mutually exclusive if A and B cannot occur at once. Mutually exclusive is synonymous with disjoint. They're the same thing. Here we see an example of mutually exclusive and conjoint. So in other words, A and B are mutually exclusive because of the fact that they share nothing in common in the first example. Whereas in the second example, in this Venn diagram, there's an intersection, so A and B are not mutually exclusive, but rather they're conjoint. So for our first three examples, the event A, and number 1, is rolling a 3 on a die, and event B is rolling a 4 on a die. These events are mutually exclusive because they could never happen at once. The probability would be 0 or impossible. In event A, randomly selecting a male student, and event B, randomly selecting a nursing major, these events are not mutually exclusive. They're conjoint because of the fact that a male student can be a nursing major and vice versa. So if these were represented in a Venn diagram, there would be an intersection. Same thing would go for number 3. The probability of selecting a blood donor with type O blood and the probability of selecting a female blood donor. A female can have type O blood and vice versa. So if they were represented in a Venn diagram, there would be an intersection. These would not be mutually exclusive. Now that you know mutually exclusive events, we come to the addition rule. The probability that events A or B will occur is given by the probability of A or, notice the or and not and like the multiplication rule, the probability of A or B equals P given A plus P, the probability of A plus the probability of B minus the probability of A and B. If the events are disjoint or mutually exclusive, then the rule is simplified and expressed as the probability of A or B equals the probability of A plus the probability of B. There would be no intersection, so we would not have minus the probability of A and B. Our intersection would equal 0, so we would just omit minus the probability of A and B. For our first example, you select a card from a standard deck. Find the probability that the card is a 4 or an ace. You roll a die and find the probability of rolling a number less than 3 or rolling an odd number. For our first question, you select a card from a standard deck. Find the probability that the card is a 4 or an ace. The events are mutually exclusive, and we would be using the simplified addition rule. The probability of a 4 or an ace equals the probability of 4 plus the probability of ace, which equals 4 out of 52 plus 4 out of 52 equals 8 out of 52. Simplified equals 2/13, which is approximately, we're rounding, 0.154. Again, There's no intersection, so the events are disjoint. For our second problem, rolling a die and finding the probability of rolling a number less than 3 or rolling an odd number, there's an intersection because 1 is less than 3, yet it's also an odd number. So this intersection forces us to use the full formula. So P is less than 3, or the probability of odd, excuse me, the probability of a number less than 3 or an odd number equals 2/6 plus 3/6 minus 1/6, our intersection, equals 4/6, simplified into 2/3, which is roughly 0.667. You've learned how to use the multiplication rule, the addition rule, disjoint events, and independent events. I'm Luke Jenna, and I really hope this video helped you.